On February 17, 2025, a 76-seat regional jet operated under the Delta Connection brand slammed into runway 23 in Toronto. The aircraft flipped completely upside down before coming to rest. Thankfully, all passengers and crew on board survived the accident. So what caused this aircraft to crash into the runway? While investigators work on an official report, an analysis of what we know so far allows for some informed speculation. The aircraft 932 X-Ray Juliet was a CRJ-900 made by Canadian aerospace company Bombardier, though Mitsubishi has since acquired the program. Having been manufactured in 2008, it was roughly middle-aged in airplane years. The plane was being operated by Endeavour Air as Delta Connection Flight 4819 from Minneapolis to Toronto. The flight was sold out, so all 76 seats were filled. The 2 pilots and 2 flight attendants brought the total on board to 80. In command was a captain that had been with Endeavour for 2 decades. Reportedly, he spent most of his time working as a simulator instructor, but kept his skills up to date by flying the Lion once in a while. The first officer had been employed by Endeavour for about 1 year. Her flight time with the company is not yet known, but she probably had several hundred hours in the CRJ. Weather in Toronto consisted of mostly cloudy skies with bases several thousand feet above the airport and prevailing visibility of 6 miles. But blowing snow significantly reduced visibility in certain spots. Winds were from 270 degrees at 28 knots, with gusts up to 36 knots reported in the middle of the day. The winds would not have made the landing easy, but they were nothing a trained crew couldn't handle. In the 15 minutes prior to the crash, 8 other aircraft landed on runway 23, including 2 Embraer 175s, which are of similar size to the CRJ-900. None of these flights reported anything out of the ordinary during their landings. ADS-B tracking data show what looks like a normal flight and approach with ground speed and descent rate consistent with an ILS approach in the reported wind conditions. The video from a Learjet holding short of the runway showed the CRJ crossing the threshold at approximately the standard height of 50 feet, with everything also appearing normal up until that point. While on a normal landing, just a second or 2 after crossing the runway threshold, the pilots will flare, meaning they will raise the nose slightly to arrest the descent and land smoothly on the main wheels. The CRJ appears to continue straight into the ground at a relatively high descent rate without any visible flare. It would be fair to say that landing a jetliner can be tricky, as it's something that takes skill which is honed through practice with the aid of experience and quick reflexes. Mistiming the flare may result in excessive landing distance, a bounce, or a hard landing. As seen in this video of a CRJ landing in Aspen, Colorado, also recorded on a windy day, the pilot flying appears to accomplish a graceful touchdown by raising the nose just in the nick of time. So the question is, did the pilots of Endeavour 4819 forget to flare? Was an attempt to flare foiled by external factors? Is the lack of the flare in the video an illusion due to distance and perspective? Well, some deeper analysis of the Learjet video can help us figure that out. We can see that the Learjet is several yellow stripes behind the red runway hold position markings. It's holding short of runway 23 at an intersecting taxiway that's just behind the runway threshold. By the way, the pavement with white arrows is a displaced threshold and all aircraft must land after the arrows. Anyway, we can estimate the Lear to be about here, but the image is blurry and the Learjet's nose and instrument panel are blocking the view of the yellow taxiway centerline stripes, so this estimate lacks precision. Fortunately, there are other objects to look at. This appears to be the windsock and it lines up with the flashing wigwag lights at the runway entrance. Furthermore, the runway hold position sign is offset slightly to the left of this object, which is probably a runway distance remaining sign. From these cues, we can extrapolate a narrow range of possible positions for the camera. It's most likely here to put it in line with the windsock and wigwag lights, but it can't be any closer to the runway than this point, which would line up the runway hold position and distance remaining signs, and it's probably not any farther back than this point, or we'd see more yellow stripes in front of the nose. As the CRJ touches down and the right wheel begins to disappear, the wheel is just in line with the runway distance sign, while the extreme aft end of the tail is lined up with the runway hold position sign. This allows us to determine the most likely touchdown locations, which could have been about here or maybe here. At the extremes, the CRJ's touchdown point could not have been any farther down the runway than this position, and it couldn't have been any closer to the start of the runway than this position. Now I know what you may be thinking. This analysis can be fraught with error. How can I be sure the objects in the crash video match the objects in the satellite photo? Well, thankfully we can analyze the video a different way. We can independently determine the CRJ's landing point by using time. We see the main wheels of the airplane cross the taxiway centerline here, and then the right main wheel disappears as it touches the ground here. That moment occurs 3.1 seconds later. The last position recorded by FlightAware was here at a ground speed of 116 knots. This seems about right when considering the wind and the flight's payload and approach speed for its landing weight, but we'll apply a plus or minus 15 knot margin of error, which should be more than enough to account for both variations in ground speed and errors in timing the video. With that ground speed estimate, the aircraft would travel between 528 and 685 feet beyond the taxiway centerline, or 364 to 521 feet past the runway threshold, putting the aircraft in this area highlighted in yellow. This verifies the earlier finding and confirms that this was the approximate location of the aircraft at touchdown, with the two magenta aircraft representing highly unlikely positions at the extreme ends of our estimates. All of this is noteworthy because the standard 3-degree glide slope intersects the runway at 950 feet past the threshold, and when accounting for the flare, jets will normally touch down about 1,000 to 1,500 feet or more down the runway. Pilots can make adjustments to this for short runways, but there's no reason to do so here. So not only did Endeavour 4819 not flare, but it struck the runway while descending at an abnormally steep angle. Since this approach had been stable, its descent angle must have actually steepened during the flight's final moments. Of course, we'll have to wait for the aircraft's flight data recorder to be analyzed to know the instantaneous descent rate at impact. But my own eyeball estimation based on the time to descend one fuselage diameter before touching down is at least 800 feet per minute. Even if there was an invisible attempt to flare at the very last moment, it is unlikely the crew got the descent rate below the aircraft's structural design limit of 600 feet per minute. I'm not sure about the CRJ, but in the jet I fly, landing at more than 360 feet per minute or 6 feet per second is considered a hard landing and requires a maintenance inspection. But why did the aircraft flip completely over? Since there was a crosswind from the right wheel touched first. This would be normal and desirable for a crosswind, but due to the large impact force, it appears the right main gear collapsed, probably because it was subjected to forces beyond its design limits. That provided a rotational moment. Why the airplane landed so hard is the key question that investigators will attempt to answer, but here are some possibilities. One candidate is a sudden change in wind, known as wind shear. The headwind component could have disappeared in the final seconds of flight, causing indicated airspeed to drop, resulting in a loss of lift and a high sink rate. While the crosswind was not out of limits and does not seem to be directly responsible, if the crew allowed the wind to carry the aircraft off the runway centerline, an inexperienced first officer acting as pilot flying may have been concentrating so hard on runway alignment she had no mental or physical capacity remaining to accomplish a flare simultaneously. Another possibility is that one or both pilots experienced spatial illusions due to snow and flat lighting. Further contributing to such a phenomenon could have been the Canadian runway looking unusual to the American crew due to differences in size and markings. All of Toronto's runways are 200 feet wide, while the majority of runways in the US are no more than 150 feet wide. The distance markings on the sides also differ between the US and Canada. I myself was once caught off guard my first time landing in Toronto, even though I had been flying for an airline for several years by that point. As I tried to judge when to begin my flare, I realized the runway looked almost alien. Fortunately, by looking around at some nearby buildings, I was able to acquire some depth perception and realize I was starting my flare too high. I was able to make adjustments and land safely. Now, even though the captain was very experienced and likely had been to Toronto before, it may have been the first officer's first time landing there, and she was probably the pilot flying, with the captain handling pilot monitoring duties since it was his voice heard on the radio. On that note, a captain who was used to SimWorld could have been a problem. Perhaps he was rusty and did not catch mistakes or deviations by the first officer, or perhaps he even gave her some bad advice that works for trainees flying a simulator but not in real life. One potential problem is that the crew did not maintain the proper approach speed all the way to the runway threshold. Based on the aircraft being heavily loaded with people, baggage, and plenty of reserve fuel, I think the aircraft's speed might have been a bit too slow. This would tend to increase the sink rate and make the flare more difficult. An unusual but not impossible problem might have been an incorrect calculation used for aircraft weight or approach speed. If something like this was a factor, we just won't know until the official report is released. A mechanical problem with the aircraft, such as a flight control problem, seems unlikely, but stranger things have happened. Several Boeing 737s crashed in the 1990s before it was discovered that an improbable sequence of events could cause the airplane's rudder to deflect in the direction opposite of that commanded by the pilots. Alternatively, a self-induced control problem such as forgetting to turn off the autopilot before landing could be to blame for Endeavour's misfortune. This accident might be compared to another hard landing accident from decades ago. When the McDonnell Douglas MD-80 was new, it had to undergo a flight testing program for certification. On one of these test flights, a crew was attempting a test meant to measure landing distance, but instead landed so hard the nose wheel collapsed, the fuselage buckled in places, and the entire tail separated. The pilots and a few passengers consisting of engineers and FAA personnel mostly walked away from the crash, but one did suffer a broken ankle. Anyway, the pilot's statements and the NTSB's remarks in its investigation yield some interesting insight into what could have been going on in the cockpit of Endeavour 4819.
At about 55 feet, the pilot perceived a slight increase in the descent rate, and therefore he decided to delay the thrust reduction. He said he thought he reduced the thrust to idle at 37 feet and began his landing flare at 20 feet. Based on his previous practice, the pilot said that the flare required definite back elevator, maybe half the available travel of the control column. However, because he still had a perception of a slightly higher sink speed, he applied more back elevator force on the control column. The aircraft landed hard, and as a result, the nose fell through and the nose wheel tires blew out. The pilot applied reverse thrust and wheel brakes and stopped the aircraft, shut the engines down, and secured the aircraft. After he left the aircraft, he saw that the empennage separated and was lying on the runway. In summary, the evidence indicated that the pilot did not allow sufficient time, distance, and altitude on final approach to stabilize his aircraft before reaching decision height. The aircraft was not stabilized on its descent. In particular, the net thrust was 5,000 pounds below the thrust required to maintain airspeed and descent rate. The pilot did not recognize that the approach was not stabilized. Although he sensed the increasing sink rate, he did not perceive its magnitude, and he did not try to verify its magnitude by cross-checking his vertical velocity indicator readout. Contributing to the cause of the accident was the lack of a requirement in the flight test procedures for other flight crew members to monitor and call out the critical flight parameters.
Like the MD-80 test pilots, the CRJ crew might not have recognized the impending disaster, and if they did, by then it might have been too late to correct it. One interesting factor in the MD-80 crash cited by the NTSB was a lack of standard operating procedures calling for a pilot monitoring to verbalize deviations from stabilized approach criteria. All airlines have established SOPs to accomplish this, but time will tell whether the Endeavour crew followed them. Whether there was wind shear, a control problem, an issue with depth perception, an incorrect weight or landing speed calculation, a rusty captain, an inexperienced first officer, a crew that didn't get along, or any number of other possibilities, how much is the crew to blame here? I think it's way too early to make that determination. But one lesson pilots can learn at this early stage is to never take a safe landing, or more generally, a safe flight for granted. Flying is still the safest mode of transportation, but only because we have developed and fine-tuned a system over many decades to eliminate as many risks as possible. That system has become a well-oiled machine, but even the best machines can break down if they aren't maintained. As aviation professionals, we must not allow ourselves to become disconnected from the fact that we must be diligent every time we come to work to ensure flying continues to be safe.